Hey guys, thank you. So welcome to my talk. So this is my first time here at NorthSec, and I'm very proud to be here today, really. This morning we've had amazing talk. I learned lots of stuff, lots of new things. It was pretty cool. So in my talk today, I have something that is pretty cool that I want to show you. Well, at least I hope you'll find it cool too. So basically, this is a project I've been working on and off for the past year or so. And every time I work on this thing, I keep learning new stuff, new tricks, new ways of doing stuff. And as a matter of fact, I have something big that is about to come out, something that is using exactly the technology that I'm describing in my talk today. But unfortunately, I haven't been able to pull it out for NorthSec. Because I need a couple more months of technical implementation and things like that. So if you follow me, you'll see what I mean. All right, so in a nutshell, I'm about to show you guys how to set up a cache timing cover channel so that two virtual machines that are co-located on the same physical box can talk together. Basically, that they can modulate a signal through the last level cache, the L3 cache. Using a technique of cache and reload, flush and reload. The technique I'm going to show you is a practical implementation. This is not just a proof of concept or theory stuff. It's something that works for real. And when I mean something that works for real, it's something that is stealth. Something that, let's say you have your backdoor installed in one of the VM, no one is going to detect it ever because it doesn't take too much CPU resources. It's really stealth. So just one thing to notice before we start. For this trick to work, your virtual machine have to be co-located on the same physical socket. They can be floating on any core. It doesn't matter as long as they are on the same physical socket. And the reason being that L3 cache is shared across sockets. It doesn't span across multiple socket machines. So if your virtual machines are co-located on hyper-threaded siblings on the same core, right? There is other trick that you can do to modulate a signal across the two VMs. For instance, here in this picture, you can use the L2 cache. You can also use the L1 cache, or you can use the CPU resources that are shared across the two hyper-threaded siblings. And actually, this is my first example I'm about to show you guys. All right. Okay, so before we begin, usual disclaimer. So this is a research thing on my own time, on my own network. This talk reflects my opinion, not the one from my employer. Information, code, and things like that, it's for educational purpose only, all right? So, yeah. All right, so let me introduce myself and also give you some context of how I ended up working on that project in the first place. So my name is Etienne Martineau. I'm from Ottawa, Canada. I work as a Linux kernel engineer for Cisco system. When I was a kid, I was really fascinated by radio and electronics and the concept of modulation and things like that. Only much later, during my electrical engineering study, I finally understand what was going on. But then after school, I got a job, ended up working on the Linux kernel, hacking around and things like that. So I totally forgot about this modulation thing up until very recently, about a year and a half ago, where part of my work, I was doing some low-level performance analysis on KVM. I noticed something strange once in a while. Basically, I saw some sort of crosstalk going on between two VMs. So I dig deeper into that problem back then, and I realized that the problem I was observing was only manifested when the two VMs were co-located on the same physical core, but two different hyper-threading pair. So then I did some more research, and I found that nice picture from Intel. So basically, this thing is showing that some operation, when you are running with hyper-threading enabled, some operation, instead of running in parallel, they have to be serialized one after the other. So that's the picture that is showing that. And so that explained the result I had. But then Then at that time, that was exactly at that time I got that idea. I said to myself, well, what if from VM number 1, let's say, I modulate a contention pattern over the execution pipeline. Let's say a long instruction multiply is a 1, a short instruction is a 0, all right? And now what if on the other VM, I try to detect that contention over the execution pipeline. So by measuring the time it takes to execute a certain instruction. If it takes long, well, it's a 1. If it's fast, then it's a 0. So this is exactly at that time that I realized that it should be possible to kind of modulate a signal across 2 VM using this contention pattern tricks. And to be honest, at that point, I was caught. So I ended up spending quite a few nights actually playing around with this thing, this pipeline contention, the phase lock loop, and a bunch of things that comes with it. I was really curious to see the nature of the communication channel. And so naturally, I decided to try to transmit an image so that I could see the resulting output on the other side, right? So obviously, this was not the first image I tried to transmit, but I repeated that exact same experiment for us here at NorthSec. So this image is a 640, 480 VGA quality, 1 bit per pixel thing. And then when I send that image to the other VM, this is the result I got. So it's all blurry. But we can still see some pattern. We can see the logo there, but you see that there is lots of noise, and yeah. So basically, at that point in time, way back then, so this is at that time that I realized that there was a big security problem with this whole technology. Because if I can do that, it means that I can probably send data, no problem, right? And yeah, by the way, before we move on to the core of my talk, I did a video. Basically, I'm repeating this experiment, but instead of just sending one picture, I'm just streaming them in real time at 15 frames per second, and then we see the effect of what's going on the system. So let's take a look at the video here. All right, so just before we begin, so on the bottom left, I have what I call my noise generator. Okay, so it's a compilation of the Linux kernel on all the processor. So this is triggering lots of noise, lots of crap is going on in the execution pipeline, and you will see the effect on the stream. The other thing I want to mention is I'm running the MP4 encoding software in order to render this video on the same machine than I'm doing the experiment. So that thing is causing lots of noise on its own. If you don't run the encoding software, it's really more clean than that. All right, let's take a look. So the stream is going on real time right now, 15 frames per second, and now I'm starting and stopping the compilation of the Linux kernel. You see that? So remember, this streaming technology is using pipeline contention. It does not have anything to do with cache. It's just a pipeline contention that is happening between two hyper-threaded siblings. All right, so let's go back to the talk here. Thank you. Okay, so now you understand where I'm coming from with this whole thing and design. It's time for us to take a step back. Okay, so my goal was to come with a practical implementation, not just some research stuff. Why? Because I wanted to prove that this is a real issue so that we have to fix it. And by the way, I mean, this is VM, right? I'm using virtual machine. It works on ESX and so on. But with container, it's even more easy, all right? It's just like VMs is the most amount of challenge, but container, it's super easy to do. So in my talk today, we will go over, I'm going to show you all the challenge involved in the design of such a communication channel. We will go over x86 shared resources. I'm going to show you what they are. And we will go over the fundamental concept behind the cache line encoding and decoding. We have to get around the hardware prefetching logic, and I'm not disabling this from the BIOS. Then there is something new that that I found recently. It's basically the CL flush instruction. There is a way, pretty nice way to abuse this instruction to basically create a bidirectional handshake for free. Then we will look at the persistency of data, the noise that is present on the host, in the guest, in the VM, and so on. Then we will also take a look at the guest to host page table deobfuscation. Sounds complex, but I'll show you what it is. It's not rocket science. At the very end, I'll show you my implementation of phase lock loop and high precision timer. This is the key aspect for that thing to work. We will go over some detection mitigation. I've got a video at the end of the talk too that basically describe a reverse shell. You'll see. All right. Let's take a look at those shared resources and how they are isolated. So with hyperthreading enabled, like I said at the very beginning, there is lots of possibility for modulation. You can do pipeline contention. This is the first example I show you guys. You can do modulation in L1, modulation in L2. Hyperthreading is typically disabled in production environment. At the bottom here, there is a link that discussed that way back then in 2005. And so for that reason, you can use the last level cache, L3 cache, to do your modulation. So now the problem is, of course, if your VMs are being assigned to different socket on large system, well, this whole L3 cache modulation technique isn't going to work. Because the L3 cache is not shared across multiple sockets. But then there is the buses that connect all the socket together in a certain way, and there is the coherency module into that thing. So you can actually do modulation using the coherency module. I've done it. It works, but that's not my talk today. I can take question offline after the talk if you want. All right. So now it's time to deep dive about the way we encode data inside the cache. So a cache line is typically 64 byte. Okay. So and here the way we do it is 1 bit corresponds to 1 cache line. So when you read a byte that is not in the cache, let's say you want to read a byte of memory that is not in the cache. Well, it's the whole cache line that is brought in from memory all the way up to the first level cache so that you can read it and get access to it. So here the basis of cache timing modulation rely on the fact that when we read memory, we can measure very accurately using the TSC counter the time it takes to read the cache. If it's fast, if it's an L1, sorry, well, it's going to be pretty quick. L2 a bit slower, L3 a bit slower, and main RAM way slower. All right? So now the trick to do the encoding is assume, again, 1 bit is 1 cache line. So you take a specific cache line, you either load it or flush it. So you load, we assume here it's a 1, and you flush, well, you assume it's a 0, right? And now for the decoding part, what you have to do is you have to access that memory where the cache line belongs to, and then you read it. You read that memory. If it comes back real fast, it means it's a 1 because it was already loaded. If it's slow, then it's a 0, right? Okay. So I guess it sounds simple, but let's dive into the core of it. So here, the first thing I have is a very simple client and server test program. There is no virtual machine in the picture at that time. Okay, it's bare metal running directly on the host. And the cache line that I'm using, they are coming directly from shared memory. Okay, so there is no address space to worry about. Shared memory cache line. So the client is actually encoding a pattern. That's the pattern that you see at the bottom here. And once the encoding is done, the client just signal on the mutex, the server wakes up, do the decoding. And here, the decoding is all messed up, but there is a clear pattern in it, but there is something weird going on, okay? So I had to take a step back, and I wrote a simple test program that flushes all the cache line from, let's say, 0 to 100, and I read them back, and I measure the latency that I'm expecting that it should be a long latency for all the cache line. And now you see the result. Some of those cache lines, they show long latency, 240, 200 plus is long latency, but lots of the other cache line in the picture, they are already loaded. So there was something else that was going on in the background here. So this is really at that time that I learned about prefetching. Okay, so prefetching, it means really bringing data or instruction from memory into the cache before they are needed. The system I was using had some fancy algorithm for L1 and L2. They are different, but at the end of the day, prefetching means those algorithms are trying to predict in advance what address will be needed in the future. So for the stale operations, during the processor just fetch those address so that it speed up the execution, hopefully, if the algorithm are good. So I just took a picture here. So the hardware prefetcher is one of those things that you can normally disable at the BIOS level. Obviously, this is not what I'm doing here because with VMs, we don't have access to the BIOS, and that will be cheating, right? So we have to find a way to work around it. So I just, experiment a couple of things, and then the trick that did it was essentially to randomize the cache line access. So I had to do the randomization within a page. And I also had to do the randomization at page level. And when I did that, it just confused the hardware prefetcher entirely. And so then at that time, I got a clean picture. So now there is another problem that I face, okay? So what happened if you wait a little bit longer before doing the decoding? Let's say you wait, and you wait. Well, we clearly see that the time from when you encode the data to the time from when you decode the data has to be very small. Otherwise, the other stuff that is running on the system will pollute the cache and erase your data totally. So in other words, the encoded data that you put in the cache will evaporate pretty quickly. So this is even more important for us when we are running in VMs. Because with VMs, there is lots of noise, okay? And believe me, I'm about to show you. So here I've done a couple of experiments, okay? So I'm using a calibrated software loop that takes exactly 2 CPU cycles to execute. And my tests consist of running that loop 100,000 times. So I'm expecting 200,000 cycles to run that loop, okay? And I'm repeating that test 1,000 times, okay? So now, if you are on the bare metal inside the kernel with all interruption disabled, this loop is going to take 200,000 cycles over and over and over again because there is nothing that disturbs the loop. There is no one that is running, okay? So now if you are in user space, just above the kernel on the host directly, there is some noise that is going on, and that's expected. Like the small spike that you see there, they are the timer interruption on a per CPU basis. And the bigger spike, they are actually the network interruption that are coming on CPU 0. Now if we go in the kernel that is running into the VM. And in that kernel, if we disable all the interruption, remember, we won't be able to disable the interruption on the host, but we will only be able to disable the interruption inside the VM. Well, then there is slightly more noise because there is an hypervisor layer that is sucking out cycle here and there. And finally, if we are in user space inside the VM, you see that there is quite a bit of noise. Because it comes from the guest kernel, the kernel that is running in the VM. It comes from the kernel on the host. All the interruption, the guest kernel has its own sets of interruption. The host has its own sets of interruption. It comes all together. There is the hypervisor and everything. By the way, if you make the math here, it looks pretty bad, but it boils down to a 2% degradation for a compute load. So it's not too bad, but still, there is lots of noise. All right, so now that you understand the noise, we know what it is, you know what the hardware prefetcher is, let's go back to our original test program, but this time we put the client and the server in different VM. And then I realized that there is another problem. So the cache line that we were using before to do modulation in L2 or in L3, those cache lines are tagged by the physical address. But in a VM, the physical address that you have has nothing to, you cannot see what's going on the host. Basically, there is another layer of translation. And then you, as this picture is showing, you don't have access to that information. So you don't know what is what from physical point of view. So this is a complex problem to solve, to try to decipher the page table from a VM. I don't think it's impossible. I've got a couple of implementation that got it almost, but that's not the talk today because we don't actually, with KSM, we don't even have to worry about this problem. That's the beauty of it. So what is KSM? So KSM is a feature in the Linux kernel. It's used with KVM. Kernel same page merging. So basically, KSM enabled the kernel on the host to scan running programs and compare their memory. Okay, and then if there is identical pages in different programs, KSM detects that condition and merge them together on just one. Okay. So, of course, I mean, if there is a program down the road that wants to modify one of those shared pages, KSM will kick in and do the unmerging. So this feature is pretty useful with virtual machine because, you know, like the guest operating system image can be shared across other guest operating system image. So you end up saving lots of memory. All right, now going back to our test program. So remember, now I have to find shared cache line across two different VMs. So I'm thinking about KSM. All right, so what I decided to do here is the client and the server, they create, let's say in memory, they create a per page unique pattern that is the same across across the client and the server. The idea is that after some time, KSM takes some time before it kicks in to do the merging. KSM will detect those pages and see, oh, those pages are the same. And so KSM will do will kick in, and it will do the page deduplication for us. So at the end of it means that those pages are going to point to the same physical address on the host, and so the cache line are shared. One more thing before I go to the next slide, side comment. With KSM, you can do pretty cool stuff, such as, let's say, for example, identifying the operating system or the application that are running beside you in the VM. All you need to do for that, really, is you load into your home memory the image of what you think is running beside you. You wait a bit, and after that, what you have to do is you basically write to that memory, and then you measure the time it takes for the write to go through. If it's slow, if it takes time, it means that you got KSM involved on the host, and then you have a match for your identification. All right. Okay, so the other problem that I realized with this scheme is there is no synchronization primitive that spawn across different VM, right? Well, in reality, there is mechanism out there. IVSHM is just one example, sorry. But this is not enabled in production environment. IVSHM, you can signal a semaphore across VMs and so on. So, we basically need something to replace the mutex that I was using to signal the server and the client. Why? Well, we want the server to run right after the client, because if we wait too long, the data that we put in the cache is going to be completely gone. So ideally, we want the client to run and the server to run right after. If we wait too long, gone. All the data is gone. Okay, so there is a couple of options that I thought through. I mean, one of them is basically, okay, I'm going to forget all about that synchronization aspect because it looks pretty complex to solve. And with some error correction set to the roof, I can probably achieve some transmission. So the idea is basically the client and the server, they are floating around in their own time space, and at some point in time, they will kind of overlap, and there will be some transmission. So it will give a very low bit rate, obviously, and also the CPU consumption is going to be low. That's good, because that's what we want. We don't want to be detected by anyone that is monitoring processes on the system, so we don't want to burn CPU. Option 2. So then the other option is basically, well, I'm just going to have a while one loop on the client side, a while one loop on the server side, and I'm just going to adjust the client to run slightly faster than the server. So at some point in time, those guys, they will kind of overlap, and when they do, it's going to provide an okay bit rate. The problem with this implementation is super high CPU utilization. I mean, anybody that monitors the system will detect that there is something wrong going on, right? So ideally, we would like to stay below 1% of CPU usage, but I'd say that 1% is still high. With the new technology I'm using, it's like more like 0.1%. Okay, option number 3 is really the option that I'm using. So this one, it basically implies that client and server, they agree on a common period, okay, T. And we set it up so that the client and the server, they lock into phase using a phase lock loop algorithm. So the idea is you have a server, it's in your backdoor VM, it's running, and it sends a sync pattern at regular interval that you have predefined. And then this sync pattern is really like what you find in vertical TV, like vertical sync, for those of you who have seen that before. And now I'm just going to make a deep dive onto that sync pattern because that's new stuff I found lately. So remember, we want things to be undetected. So our server that is sending that sync pattern, we don't want that guy to suck CPU, right? We want our sync pattern to be pretty efficient. Ideally, 0.1% would be the best thing. But how the client will detect that sync pattern in that whole noise and stuff like that is a challenge. So this is where I bring the magic of CL flush. I'm implementing a bidirectional handshake with this one. CL flush instruction it's an x86 instruction. This thing is normally used to flush a specific cache line so that the other guy that is running on the other side can measure if that cache line is loaded or not. So here, the idea I had is I'm using CL flush in a different fashion. Instead, I'm measuring the time it takes to run the CL flush instruction. And then if you think about the microcode, this is just pure speculation here, but I mean it works with the model. The microcode of the CL flush instruction, probably the first thing it does, it basically, oh, is this page valid? Yes or no? Yes, it is valid. All right, next thing, is this cache line loaded or not? Yes or no? Well, no, return right away. That's the fast path. Yes, run the eviction algorithm. That's the slow path, okay? So the trick here for the synchronization that I'm doing, it's basically on the server side, I do CL flush, 4 times, let's say, okay? 4 times CL flush. So every time I run that instruction, I expect the time to run that instruction to be small, right? And on the RX side, what I do is I basically load this cache line, load this cache line, load this cache line, and load this cache line. So I expect that to be fast. The only condition where this thing is not going to hold true is if the two guys are perfectly in sync, one on top of the other. Okay? There is no way that the noise on the system can generate such a pattern because the TX is basically running 4 CL flush instructions in a row, spread apart by 200, let's say, cycle. So there is no way that another program out there will access that same cache line and flush it and load it 4 times in a row. It's almost impossible. Only the RX side can do that. So that's why it's a pretty efficient sync pattern. Okay, so like I was saying, so now we have the sync pattern. It's pretty efficient. So the thing that is going on is the client. This is the machine that we control. That's the VM that belongs to us. We own that VM. That's the backdoor on the other side. And so that guy is doing a sweep scan and basically look at the noise going on. He's seeking for this sync pattern, okay, over and over again. I don't care how much CPU that guys burn. It's my VM. I control whatever, okay? So once the client is basically finding the sync pattern that the server is using, he's basically locking on the phase. And this is where we can do our transmission. But the big problem I had, and that's the key aspect to my design, is for that whole thing to work, we have to have a monotonic pulse, okay? It means that really, I mean, like the server and the client, they have to stay kind of in phase. So if you are using a timer, you have to come back always at the same time, so in order to keep the sync. You can tolerate some jitter, but not too much, because remember, all the data that we put in the cache will go out very quickly. So the problem is, how can we achieve a monotonic pulse with Linux, let's say, or Windows? I mean, the first thing that comes into mind is to use timers. All right, so timers are good because we need to sleep, right? So we can define a period so that over that period of time, we just burn 1% of CPU. But there is a big problem with timers. There is jitters with timers. There is lots of jitters. This is a frequency distribution graph, log scale. And as you can see, with timers, there is lots of jitters in the order of 100 microseconds, for example. Actually, to be fair, this is pretty good data. I mean, I'm running this test in a VM, Linux is running on the gas in the host and so on. So I'm really amazed how small it is. But for the stuff that we are trying to do here, that's way too much. So on top of this, you have the jitter. I mean, like both client and server, they are subject to the same jitter, right? So that's going to be way too much. I mean, they're going to go like all over the place. So the idea I had is to basically compensate those timer in software using to some value that goes above something I define the maximum jitter. So in theory, this should give us a nice monotonic signal. There is one catch here, is you have to be very careful with this, because the compensation, whatever type of compensation that you do, is subject to noise. So in other words, what I'm trying to say here is more time you spend trying to immunize yourself to noise, more noise you end up accumulating. So, and obviously also, it's the compensation on its own will burn CPU, but that's fine. I mean, all we have to do is to stretch the timer period to something bigger, and then we can compensate into this one. It's a tricky problem. At the end, I got it right. So in short, the compensation algorithm is using a calibrated software loop that is kept in check at every single point in time with the TSC. This is the result I got. Okay, so that's my 2.4 gig machine. And on an idle system, the jitter I have on my timers is in the order of 50 cycles. On a loaded system, it goes to 300 cycles. I mean, if you compare that with the stock implementation, the stock implementation was giving 240,000 cycles, best case 24,000 cycles. I mean, that was way out of bounds. So this 300 cycles, 50 cycles, this is the stuff that we need to be able to transmit data over cache. So I'm putting the data in perspective with the original latency graph here. As you can see, it doesn't even show up on the scale. And as you may already understand, this synchronization aspect is really the key behind this design. It enables communication to happen with very low noise, and at the same time, it consumes just a fraction of the CPU. Okay, so now I'm going to recap what we have so far. So we have an encoding and a decoding scheme based on memory access time. 1 is a slow, 0 is fast. We managed to get rid of the hardware prefetching logic without fooling around with BIOS. We found some physical cache lines that are shared across VMs thanks to KSM. Now I'm sure some people here are asking themselves, well, what if KSM is not enabled and so on? No worries. I mean, the cache has an associativity level. So if we don't use KSM, we can still rely on the cache associativity to do the encoding. It takes a bit more CPU to do, but I mean, really, I mean, from the result I have, it doesn't make a whole bunch of a difference. We have a very efficient way to synchronize the client and the server. We have a phase lock loop that maintains the phase and the inter-VM synchronization, less than 120 nanoseconds apart. Okay, all right, that's time. This is now time for a demo. Okay, so so this is, let me just look into this one for a second. So this is the original experiment that I did at the very beginning. At the very beginning, I was using pipeline contention. You remember all the noise that was coming on the other side? It was pretty ugly. So now with this cache, last level cache modulation, I can achieve much better result. You can see that, I mean, you can obviously see that there is noise on the channel, but this is expected. Look, I'm not doing any error correction here whatsoever. So, but the noise level is pretty low, I would say. Then what I did in this video is basically I repeated the streaming experiment, but this time it's with this cache techniques. Okay. So the first thing that I want to mention is, and that's kind of cool, is basically when the transmitter, okay, the transmitter is on the left-hand side. So when the transmitter is not running, the receiver is picking up on whatever is running on the system. He's basically picking up the noise of the underlying system. And to me, this is pretty cool. So right now you see, like in this picture on the right-hand side, it's like crappy noisy, but this is because of the MP4 encoding software that is running. That guy is generating lots of noise. If you take this out, I should have taken a video from my phone. You see that it's pretty clear, the pattern that is coming out of this noise. And as a matter of fact, if you do a frequency analysis of that noise, it gives you a spectral signature of the underlying operating system that is running at the host level. So you can find out, assuming you have a database to compare to, who is running on the host with a very, very high level of accuracy. And this is the type of stuff I'm working on these days, and I wanted to pull it for today, but unfortunately I haven't had a chance. All right, so let's look at the video. One last thing, there is no compression, no error correction. It's raw data that is going on. So again, I've got that noise generator that is running in the background, compilation of Linux kernel on the bottom left window. Let's take a look. All right, so you see the noise. So that's the video encoding software that is generating so much noise. Now when I start the Linux kernel, you see it becomes white because there is so much noise in the cache. All the cache is being evicted all the time. I mean, lots of file access, lots of CPU operation. It's obvious. And now if I start the transmitter, okay, so the transmitter is on the left-hand side. You see what is being received on the other side. You see that there is noise, and actually this noise is triggered by the MP4 encoding software. But if you look when I start the compilation of Linux kernel, you see like lots of background noise going on. All right, so let's go back to the slide deck. Thank you. All right, so if you make the math about the bandwidth here, so this video was transmit VGA quality, 1 bit per pixel. It was interlaced 4 times, 15 full frame per second. 1 frame is this quality, 1 bit per pixel. It boils down to roughly 4.5 megabits a second. Both sides are using 50% of a CPU, so I could crank it, I could double that essentially. All right. So now it's time to look at something a bit more useful than trying to stream data out. So this is really the reverse shell example I was describing to you guys. So first thing that I'm doing in this experiment. So the two windows, basically they are like, on the top, they are two different VM, obviously. And so the first thing I'm doing is I'm running the server in loopback mode. What does that mean? It means essentially that the server doesn't process the command. He's basically just dumping whatever the client is sending. So client happens to send hexadecimal A. So you'll see what's going on here, okay? I'm launching. All right. Okay, so the server is running in loopback mode. The client is also running in loopback mode. So the client is, so this is the search for the sink. Then there is a lock, and the client is sending. So now the server receives stuff, but you see that there is crap in whatever the server is receiving. That's expected. There is a couple of bits turned on. Compilation of Linux kernel, trigger more noise. Again, that's expected. So now I'm repeating the same experiment, but in this in my program I have what we call forward error correction, ECC. So I'm turning on ECC -capital F, and with ECC things should be corrected, right? So the server is running on the left-hand side. Client, I'm just going to start the client with forward error correction, enable, and we should see that things are clean, right? Yeah, obviously things are clean because errors are auto-corrected by the forward error correction, read Solomon. Obviously, if there is more noise than what the error correction can do, the program will display like, star, because it basically cannot auto-correct so many bits. I'm just using, for parity, I'm using actually just 16-bit. For this one, I'm just using 16-bit ECC for 240-bit payload. So in theory, I just could crank this to the roof, and that will make it more resilient to the noise. So now I'm removing the loopback, and I'm going to run the server in reverse shell mode so that the client can execute command on the other side. So when this thing happens, the server does not burn CPU. So I'm running command on the right-hand side, and the reverse shell on the other side is responding to me. I'm looking at the process that are running on the other VM right now. That's the timing channel guys that is running on the other VM. He's running the server shell. I'm going to dump a file right now. That's part of the source code for this timing channel, one of the file. So yeah, basically that's the reverse shell that is going on. I'm just doing exit. The exit is going to exit on the server side, obviously. All right, so that was the reverse shell example. Let's go back here to the slide. Okay, sorry. Okay, so now the thing is, what can we do, to avoid that type of stuff, okay? So first thing, disable your KSM, okay? Actually, newer implementation of the kernel, they don't do page DDoP across VMs, so that's fine, per VM policy, essentially. So you get rid of the inter-VM shared page, good stuff. So your flush and reload won't work, not for free at least. And then so you won't be able to do OS applications fingerprinting, but you will suffer higher memory costs for that. The defense, my stuff I'm doing, if someone does that, well, I'll say, okay, forget KSM, we will work at the cache set level instead. So I don't need page DDoP. It's a bit more expensive, but you have to run a couple of algorithms to find your set, merge the set, and so on. So typically you have 16 set to work with instead of just one. So one of the other thing that needs to be done, to my opinion, CL flush, I mean, it leaks all over the place. I like measuring the time it takes to do CL flush instruction and deriving data out of that is pretty bad. It's pretty efficient for me, but it's pretty bad for system. And for fingerprinting, it's no good. Okay, very secure system. You should think about your co-location policy. I was talking to someone at lunchtime about that. You know, you have containers, VMs, you're co-located with other other folks, you don't know about them. So if you really want a secure environment, think twice about that. I suggest you basically get the whole box to yourself. There is a couple of things we can do from the detection point of view. One of them is there is hardware counters that exist on the chip, so you can do pattern and noise analysis. I've got some prototype. It's okay, but it sucks CPU on the host. One of the other thing is on the host, those processes that are run, they are running exactly always at the same time for that to work. So in theory, we can set some heuristic in the kernel to detect those type of scheduling pattern. Abnormal TSC usage is another thing. Read TSC, this type of, my implementation is using lots of read TSC to set up the timing and so on. So, I mean, like if there is abnormal TSC usage, red flag. All right, that's all I had, guys. So thank you very much for attending.